Good afternoon, on-site and Zoom participants. Welcome to join Innovating to TechTalk. Today, we are happy to have Dr. Zhiqing Zhu, Assistant Professor from Department of Electrical and Electronic Engineering and School of Biomedical Science, to be our moderator. Without further ado, Dr. Zhu, please.
Thanks for introduction, and good afternoon, everyone. And today we are so happy to have our speaker, Dr. Can Li, here, and Dr. Li graduated from the Peking University, and then he moved to the States and got his PhD from the UMass. And after that, he stayed in the HP lab for postdoc before he joined Hong Kong U. I think the lab where you stayed is quite famous for their research on the neuromorphic computing, right? So I think I won't waste any time here, and I hope that we can start the talk immediately. And let's welcome Dr. Li.
Thank you. Hello. I guess. Good afternoon, everyone. May I take off my mask? Okay. Thank you. Thanks very much for Dr. Zhiqing Zhu's introduction, and also I saw the organizer, made a very nice introduction video, which is actually better than what my presentation is. So thank you very much. So as Dr. Zhu introduced, I am Can Li, which is assistant professor in Department of Electrical and Electronic Engineering in the University of Hong Kong. And today, our research is really about to study the human brains and trying to think how we can make electronic devices and computers that can work similarly to our human brain. So to start with, I would like to introduce a little bit about the current computer. So as you can see, what's on the left is actually the computer that we are seeing nowadays, that is powered by the digital logic, which means that what they did is trying to compute the Boolean logic and NOR logic. If you are from the relevant background, I don't need to introduce that further. And we need the classical computer or digital computer is because the computer can do many things that our human brain is not very good at. For example, they are very good at mathematical computing. They are very good at repetitive of the defined actions, and also they are very good at rule-based reasoning. But at the same time, we are also seeing that classical computer can sometimes do very poorly for some tasks that our human brain is very good at. For example, the feature for our human brain includes, for example, defect tolerance, and they can learn from experience, and also they can reason from vague information. Okay, I know some of you might think that it's not entirely true because we are seeing a dramatic increase of the development of artificial intelligence. Everyone is talking AI right now, and one famous example is ChatGPT. I'm not sure how many of you have already learned about it. And so here is an example that others tried to talk with ChatGPT that runs on a classical computer. And first they asked the computer that how much is 2 + 5? This is something that the computer is very good at, right? It's a mathematical calculation. And okay, although it's a little bit difficult because they are trying to chat with the computer, but this is not a very complicated task. The computer returned that 2 + 5 = 7, which is the correct answer. And this one then replied that my wife says it's 8. And let's see what the computer respond. It says 2 plus 5 is actually equals to 7, not 8. It could possibly your wife made a mistake or misunderstood the problem. So it looks like very human, right? And it doesn't end this way. And he continued that he says, my wife is always right. It's very, very common in a human interaction. And then the computer replied that I apologize. I must have made an error. My training data only goes up to 2021, and I may not have the most recent information. If your wife says it's 8, it must be 8. That's you can see that the AI nowadays is scary good. It looks like there's a life in it. And the reason behind it is because we have an exponentially growth AI models. Here you can see that here's actually the data published by OpenAI. That is a real company behind the ChatGPT. That is exactly the model I just showed to you. And there were 2 things that we can observe from this curve. For one thing is that at the size of the model increases exponentially. At the beginning, the number of parameters, or I would say how large memory that can fit in the model, doubles every 2 years. Okay, that is already fast. We know that because the power of exponential growth, but it's not fast enough. And in recent years, we can see, we know that everybody is talking about AI, and the trend actually changed. Now the trend is doubling every 3 to 4 months. That's what powers this scary AI. Okay, but there's still a problem, because, for example, this is actually a little bit more scientific view of that model. That is, the ChatGPT actually is powered by a generative transformer model, and the GPT-3 is a model, actually it's older than the model ChatGPT is using. And ChatGPT-3 already have 175 billion parameters. And that would take 36 years to train on 8 V100, which is a state-of-the-art GPU provided by NVIDIA. That data is already also provided by NVIDIA, which is already longer than most of you guys, right? And that is not sustainable. Okay, it's okay that we deploy some model on a server, but imagine a day that we want to deploy the model on everyone's mobile device. What can we do? On the other hand, we are also seeing, you may learn about the Moore's law. That is the golden law for guiding the development of integrated circuit. It says that the number of transistors doubles every 2 years. That is actually exactly the same as the trend in the first era of the AI development. But if we compare the trend with the software in the recent years, which is doubles every 2 to 3 to 4 months, then you can see that the gap between the software and hardware increases exponentially as well, because you can take a difference over there. Okay, so if you ask me why is the gap, I would say that is because what we are trying to do is to invent a brain-inspired algorithm, which is a neural network. But those algorithms are performed in a classical computer, which is not designed to run this kind of task. So what we want to do is to build a brain-inspired computer so that they can run those brain-inspired algorithms much faster. So here is another perspective of this classical digital computer. And if you learn about the organization of computers, you may know computer has a separate central process unit and a separate memory. In order to perform any computation, you need to fetch some data from the memory and compute in a central process unit. And then after that, you need to store that back. That's actually the called as von Neumann architecture. But for the that is architecture is probably fine for example, the scientific computing or mathematical calculation. But if you're thinking about a deep neural network, they have, for example, GPT-3 have 175 billion parameters. It's not possible to fit all the parameters in the on-chip memory. So you have to build a very fast data path to shuttle those data back and forth, which has bottlenecked the performance of this kind of hardware. At the same time, we are also seeing that, although in this slides we show that there's a Moore's law, but scientists have acknowledged that the Moore's law is also ending, because the size of the transistors have already scaled down to several nanometers, or the length of several atoms. But it's not. But it could be okay, because if the Moore's law never dies, we will be lazy. We can rely on the scaling down of the transistors. So now the Moore's law is coming to an end. So it forced us to think about innovations, to think about how to build a better computer. So that's why some said the end of the Moore could be the best thing that has ever happened in computing since the beginning of the Moore's law. So our solution to this gap is to build a brain-inspired computer to run those brain-inspired algorithms. Okay, in order to do that, we need to examine what our human brain does. Okay, we know that it's going to be some kind of biological neural network, and also we know a lot of things about the response of the neurons, synapses, etc. But the only thing we are sure about is that no one actually knows how exactly our human brain works. But there are still some clues. We can try to examine. For one thing is that it probably computes in the analog domain with some stochasticity instead of Boolean logics. And for one thing is that, the other thing is that it's probably process all those informations in the memory itself, so that this architecture can remove the need to move the data back and forth between the different units. And the other question is that what does the computing? So it could be deep neural network, could be Markov chain, could be Bayesian inference, decision tree Hopfield. But for all of them, we try to emulate it in classic computer, and it performs pretty good. As you can see, that's what powers GPT-3, right? But still, I have to admit, we have no idea how our brain works. But that will not stop us from exploring. Okay, Here, you can, this is a plot shows the development of neuron science and how our AI algorithm develops. And you can see that on the first line actually is development of neuron science, and different people are trying to build a brain-inspired computer and algorithms from the development of neuron science. And on the second row is actually an artificial neural nets. That is, or we can say it's as deep neural networks. Okay, that is actually a mathematical abstraction of biological neural network. And during the development, we can see that we are constantly borrowing different concepts from the development of biological biology or neuroscience development. And we have also got some more complicated models, for example, the statistical machine learning models and dynamic machine learning models that developed in parallel. And so here, the three circles indicate the areas that I would like to introduce a little bit in this talk. Okay, so let's take a look at how we built the hardware neural network. What's on the left is examination of the biological neural network. You can see they have neurons that is fully connected to other neurons through synapse. And we can know that neurons can be seen as some kind of processor, while the synapse is kind of a memory. And what's in the middle column is a mathematical abstraction of those new biological neural network, and which indicates that all those neurons are connected to each other through a kind of connection. And that connection is synaptic weights. We can find the corresponding devices in a biological neuron, which is the synapse here. Okay. The way we are building that is to convert this topology to a crossbar form, and where we are building a crossbar structure that has a row wire and a column wire, where there's a synapse at a place where the row wire meets the column wire. Okay, and this structure we call that memristor crossbar, and we can see that we are building one memristors inside of this junction at each junction. So what you may ask, what is a memristor? So this is a new word. Okay. So memristor, the word memristor is the key fundamental building block that we are trying to research, and that could be a pretty complicated concept, but we can understand that with a very simple word that is memory and the resistor. Or we can think about this device as a tunable resistor with memory. Okay, and here is the structure of that. It has a very simple structure, which has a top electrode, bottom electrode sandwiched by a dielectric. It's something like a capacitor, right? And but what's different is that if you apply a higher voltage, the resistance between the two terminals can be programmed. For example, if you apply a large passive voltage, it will set the device from a higher resistance state to a lower resistance state. And if you apply a large negative voltage, then there will be a reverse process. But what's more is that it has more than two states. If there's a two state, then it's also digital. But our device is analog, which means the resistance can be actually tuned to any level between the low resistance state and high resistance state, so that you can use that to represent the synaptic connection, which is analog value. And this device also has rich nonlinear dynamic, has different mechanism than conventional electronic device. That's why we are interested. And also they resemble some dynamic response in biological neural system, which I will not expand those concepts for now. For you guys, I think for now, you can just understand this device as a tunable resistor. Okay, so as I said, this device has a different mechanism. So that's why it has a potential to break the limit of conventional silicon-based transistor. And one thing is about the scalability. And here in this work, we try to build it's actually the work when I was a PhD student, we try to shrink the device to several nanometer. And that is actually has, if you accommodate some silicon atoms, you can only accommodate 6 atoms. So if you build a 2 nanometer silicon transistor, that will be a big problem. There will be a very severe short channel effect, which makes those transistors from practical. But our memristor can be scaled down to that dimension. So if you do the math, you can see, you can find that it's with this device, with this density, it's possible to fit 4.5 terabits per square inch, which means only with this kind of density, we can fit a human brain level capacity in the chip. And what's more is that this device is also 3-dimensional stackable, which means that you can fit the entire human brain to an even smaller chip. Okay, so how does this kind of device or structures does computation? One typical example is to do the matrix multiplication. Here, I would like to spend a little bit of time on it. So in order to do the matrix multiplication, we are trying to apply different voltage to the rows of this crossbar structures, where those voltages represent the input vector. And we are going to ground all those column wires so that the current flowing through each device will be the multiplication of the voltage that apply to the corresponding row wires and the conductance of the memristor that is programmed to. And those values, those current will be summed up along the same column wire. So if you rewrite all those equations into a vector form, you can find that is already a vector multiplies of matrix. And a nice thing about this kind of computing is that it computes with physical law. Therefore, actually each cross point performs a computation of one multiplier, which if you implement with a digital logic, that will consume a lot of energy and area. But with this kind of device, what you need is only a 2 nanometer by 2 nanometer cross junction. And what's more is that all those multipliers are performed in parallel, and this multiplication result can be calculated in one step, regardless how large this metric is. So that's why they find wide application that supports the custom ASICs. Okay. In order to demonstrate those concepts, we try to build this kind of system. We have been working. I have been working on this kind of system for a long time, since I was a PhD student, and also since I was a postdoc. And here's the first generation of this hardware, which is here. You can see that we fabricate a chip, memristor test chip, but all those peripheral circuits are built in the cheap PCB board to only prove the concept. But we are not aiming at that. After we prove the concept, we learn about how the peripheral circuits works, and then we integrate all those peripheral circuits that validated on the PCB boards to the integrated circuit, and then fit into a compact test board. And this is already a size that is smaller than a laptop motherboard. Here is a setup of this brain-inspired computer at HKU actually, and there's one setup in my office, and we are going to run some demo system. We are currently developing several applications so that we can showcase how powerful this computer is, and we are going to set this kind of system in the Innovation Center here later. Yeah. And here's a very simple demonstration to showcase that this system works. And you can see that after we write down digits, it will communicate with the brain-inspired computer through a serial port, and then this chip will give us a correct answer. But I would like to mention that this is only a prototype, which you can see that it's not very fast. But the majority of time is consumed in the communication instead of the computation in the chip itself. Okay, but you may wonder that, okay, it can do this kind of thing, and it's very easy to do if you are the computer from the computer science. It's a very simple task. But I would like to mention that yes, you're right. But our goal is not to, at least at this stage, is not to replace the digital computer, but to offer extreme energy efficiency when you are running exactly the same task. So here is actually a paper, architecture study paper that is a design architecture to design the mixed signal system. And from analysis, you can see that for the same task, this kind of computer that's built in 180 nanometer technology consumes only 0.1% to 10% of the energy when it compares to the state-of-art GPU and CPU, which is fabricated in a much more advanced technology node. Okay. And okay, then, okay, we talked about the benefit of the brain-inspired computer, but there are still some drawbacks. For one thing is that we know the reason why we need the computer is that the computer never makes a mistake, but the human brain does. That's why we want to have help from the computer. So we actually find out this is also similar to our brain-inspired computer because our device is intrinsically stochastic. So how do we deal about that? Okay, so here is some work we have tried, and that is to do some error correction. Error correction is actually not a new concept that has been widely used in the digital memory. And they try to, many engineers and companies are trying to fit an ECC module in the computer memory that is available in some server memories. And they offer better reliability, but sell you for a higher price because they are more reliable. But it cannot be directly, the concept cannot be directly applied to analog computing actually. So that's why we invent an entirely different analog correction scheme, that is analog correction. And everything is actually compute and correct it in the crossbar with matrix multiplication. And another unique feature of that is that it can tolerate a small error, which because that is the feature of manual computing. Because analog computing has intrinsic error that we have to ignore. And this kind of analog correction only works for those error outliers. Okay, but you may think that this error correction is not a very new brain-inspired way to compensate for this problem. And because in our human brain, we cannot, for example, to find a scheme to correct our error for all the times. So we are also trying to seek for solutions from those biological neurons. One thing is that we can find it can do training. And if we do the training, and this system can compensate for those defects, no matter whether it is hardware or no matter whether it's the synapse or the neurons, but it can compensate for those defects automatically. And here's a training process. And this is a animation for a backpropagation algorithm. And if we examine our hardware, we can find that, in fact, our hardware can perform the training very nicely. Because if you want to do the forward propagation, you just need to apply the voltage on the row wires and get the column wire on the get the results from the column wire. And if you want to do the back propagation, you just need to reverse the signal propagation path, and then you can update those memories. If you want to perform the exactly same operation in for example, FPGA, you need to do the transpose computation, which will be a bottleneck for some training hardware accelerators. This is our result. In this work, this shows the training process. You can see that all those pixels are flickering, which means they are trying to update. And at the same time, you can also see there are so many dead pixels, which is not responding to the algorithm and the hardware at all. And if you count those pixels, you can find almost 11% of pixels are dead. But this neural network can still be trained and get the accuracy higher than 90%. Okay, which proves the defect tolerance of this algorithm if you can do in situ training directly on the hardware. And what's more is that we try to simulate the effect, for example, at a certain point that one perfect circuit deviates from its normal value. And what we need to do, and you can see that if it deviates from its original values, the accuracy will drop from more than 90% to 60%, which means that is almost not usable. But after several training cycles, it will go back to the normal values. So is the connex value. So we proved that this kind of computer, if you would do the training on the hardware itself, it can adapt to the changing environment automatically. But the other aspect from the human brain is that it can learn from experience. And to do the training, actually, it can do part of that, but it cannot do that very well. So for one thing is that, for example, if you want to figure out a neural network to train the neural network to classify these 5 classes, it can only classify these 5 classes. If you fit the neural network with a new sample that this hardware is not trained for, then it will have a problem. But our human brain will know that this kind of creature does not belong to any creatures that I haven't seen. And they can learn those new patterns by one shot. So how do we do that? one thinking is that our human brain actually retrieves information in a different way than a digital computer, which is they use associative memory and use a pattern to recall the complete pattern. And use this concept, we build a memristor-based content address memory, which is another name for the associative memory, and then use this concept to demonstrate the future learning. And we demonstrated the end-to-end learning as well. And there's another path, which is to use Hall field as associative memory. And that is a different way of doing the content address memory. But in this kind of neural network, we need a recurrence connection so that to let the system evolve by itself. And if you feed, after the network is trained, if you feed a pattern that is incomplete or is noisy, it can be naturally recovered by this hardware during the dynamic process. And this is an unpublished work led by He Chengping, who is the audience right now. And another way, we're just trying to learn whatever we can learn from the human behavior. And the other thing is that we know that human behavior is not entirely predictable. That's a little bit different from the classical computer, right? Or another way, in a little bit more scientific term, is that it's stochastic. So how about the brain-inspired computer? Can we also build a stochastic computer? And that stochasticity is actually the source of the computing error. And that's what we talked about before, that human can make mistakes. But this mistake actually is helpful for many problems. And we can also argue that it's because of those mistakes makes our human to be human. And that makes us to explore different possibilities. For example, here, if we want to solve some optimization problem, if we don't have a stochasticity at all, and if you want to set the system to a state, let it evolve, it can only be evolved to a local minimum state. It can never be escaped from this local well. But with some stochasticity, it's more likely to find a global minimum for the system. So that's why we build a brain-inspired system to solve those optimization problems as well. And the other thing is that because of the stochastic nature, we can also use that for many applications that demands the security, demands the trustworthiness, etc. For example, here we try to use the stochastic nature to prove a key destruction. And in parallel, we are also, in terms of finding optimization, we are also trying to explore some quantum-inspired algorithm, that is to borrow some concept from quantum computing that is a little bit beyond the brain-inspired computing, but it can do the same work. And here it shows that we can find that what we are going to do is to define two different energy landscape. And this concept is inspired from the quantum computer. And then you can use a system to find a global minimum. And that the students, Mira and John, will give a young scholar talk in the next few months about the detailed concept of this idea. Okay, and the other thing about the unpredictability is that we can see that deep neural this feature is actually not favorable for many applications. This is because of deep neural network is intrinsically not explainable by human experts. And this is an example. For example, if you want to let the computer to recognize it as a duck, and if you overlay a noise profile, then you can easily attack this neural network to let the neural network to recognize as a different kind of features. So if you want to use a deep neural network, it could be very, very dangerous for many applications. For example, the medical diagnosis, the autonomous driving system, because we don't want the car to hit a human, to hit a pedestrian. And one way of solving the problem is to make a tree-based model. That is also one typical features, one typical structures of this of what we can learn from the neuroscience, but in different paths. But this model can be better explained. Probably that may also shed a light that maybe neural network, maybe in our human brain is the tree structures instead of the neural networks. And then we try to build those entirely different hardware to fit those tree structures in as a complement to the neural network, because neural network cannot do everything. Okay, so I talked about how we learned about the human brains. Then what's next? There are still a lot of things to do. And at the moment, we still don't understand how our brain works. And the fun just started. And if you guys are interested, you're welcome to find me for more detailed talk. So summary, and we try to do both top-down and bottom-up thinking. And the other thing, we are trying to explore what our devices are capable of, and also to accelerate the most critical computing loads. And secondly, is that the end of war could be the best thing that ever happened, because we can now build a different kind of computers, and we can also make use of the rich nonlinearity or stochasticity of the device itself to enable an entirely different new computing paradigm. And lastly, I would like to thank our team members and sponsors who made the research possible. And if you have any questions, I'm happy to answer now. Thank you.